Hello friends. So in this video we are going to see about the allocation of frames, that is how many frames should be allocated for a process to fit in the different pages, and we are going to see the accesses of these pages, non-uniform accesses, and what are the different methods for allocation and thrashing. So allocation of frames in this is how many frames should be allocated for a process. So suppose we are allocating maximum number of frames. If that particular process is not using all those frames, then the free frames will be wasted there. And suppose we are allocating very less number of frames. So when we are allocating very less number of frames, what will happen? Page faults goes on increasing because there are no free frames. Page fault happens and page replacement has to take place. So neither more nor less. Minimum number of frames should be allocated. For the good performance and increasing the throughput, minimum number of frames should be allocated. Now let us consider an example here. So we are having a machine instruction in which it is making a memory reference. So we are having what? A machine instruction. To store this machine instruction, one frame is required, and to make a memory reference, whatever the data is get from the memory, to store the data, one of the frame is required. So this is 2 is the minimum number of frames required. Suppose in this condition, for this memory reference, if we are using indirect memory reference, means what? The address of the actual location is stored in a register. So again we may require a new frame to store the indirection here. So means we are increasing the frame number here. So in that, whenever we are having this one indirection memory location access, that more number of frames will be required. And if we are allocating minimum number of frames also, if this indirection of a memory access happens, then page fault starts occurring. Then it leads to many page faults subsequently. So how do we overcome this? We can overcome this situation by limiting the indirection. So what we have to do is indirection should be limited to a certain level. Then only we can control the page faults when the minimum number of frames to be given here. So then this is a basic concept here. So now there are again different algorithms for the allocation of frames. One very simple algorithm is equal allocation. Equal allocation means what? Suppose there are m free frames available. Distribute those m free frames among the n number of processes equally. So this is an equal amount of share. So what is the advantage of this allocation algorithm is it is very simple. This algorithm is very simple for implementing. Just we are doing the distribution of the frames among the n number of processes. But what is the disadvantage? To know what is the disadvantage, let us see an example. So there are two processes here. One process is just a 10 KB, means we will take 10 pages, and another is a 127 KB. So 127 pages are required here. So here 10 pages. So if you allocate 10 frames, and here if you want here 127 frames. And suppose there are 62 free frames here. Okay, there are 62 free frames. If we do equal allocation, what will happen? 31 frames will be given for both the processes. Among 31 frames, the first process is only taking the 10 frames. What about the remaining frames? They will be wasted. But then if only 31 frames are given to this, it is requiring more frames because it is having 127 pages. Only 31 frames will be given here. So it will be here wastage. In the first process it is wasting the free frames, and here it is requiring more frames. So this is the disadvantage of the equal allocation, where few frames may be wasted or the frames may be undergiven. Okay, so where requirement will increase. So this is a disadvantage here. So to overcome what we are going for the proportional allocation. So we are going for the proportional allocation. So what we are doing in this proportional allocation, we are having an equation. We are finding out how many minimum number of frames should be allocated to a process depending upon its requirement. So how to find the requirement? We are having a equation here AI. AI is the number of frames required by that process is equal to SI. SI here is the requirement of that particular process divided by S. S is the summation of all the processes requirements is into M. M is the number of free frames. So what is this S? S is given by summation of requirements of all the processes. Now let us see one example and find out how we are doing this proportional allocation. So here we are having two processes. One requires 10 pages and another requires 127 pages here. And the number of available free frames M is equal to 62 frames. Then let us substitute this. Process 1 and process 2 are there. So A1. So SI means what is the requirement of this particular process? It is 10. 10 divided by SI. Yes. What is S? It is a summation of all the processes. How many processes are there? Only two processes. What is the requirement here? 127 and 10. Total summation is 127 plus 10 into free frames M is equal to 62 here. So approximately this will become 4 and substituting the same one for the second process. The second process requires 127 pages and its SI will be 127 plus 10 into 62. Approximately 57. See here, so proportional allocation means, so this A1 is having, A1 should be allocated 4 frames and A2 should be allocated 57 frames approximately. So 62 frames are divided in this manner by giving the proportionate. This will control the page faults and also increase the throughput here. So minimum number of frames should be allocated. So next concept we are going to see about the global and local allocation. So now when we are doing the page replacement, so we are going to select a victim. So which victim to be selected? Either it should be a global victim or a local victim. So what do you mean by a global victim? See, whenever a page is to be replaced, free frames should be found. So to find a free frame in the global replacement, frames of all the processes are considered. Global means everything. So the frames of all the processes will be considered here, and from all those processes, one frame is selected as a victim here. Maybe that frame is currently being used by another process. No matter it is used or not used by another process, in global replacement, the frame is selected from a set of all the frames of all the processes. So this is called as a global replacement. Example here. So whenever a higher priority process is allowed, comes into the system, what that higher priority process will do is it will select a frame of among its own frames also all the lower priority processes. Means it is like a reserved category here. So it can take the frames from its own category, also from the other categories here. So it can take the frames from all the processes which are present in that particular system. So what is the result of this global replacement? So if that particular frame is taken from the other process which it is currently using, that particular frame will do a page fault other process it was currently using it, but still this process has taken that. So a page fault will occur by the other process here. So this process goes on continuing. That is, if you are taking the frame from the or any other process, that process may be hindered. The efficiency of that process may be hindered. Means it will go on executing slowly because it is not having a free frame. It will cause the page fault here. So again, that frame will take the frame of some other process. So this process goes on continuing in the global replacement. The number of page fault is uncontrollable in this global replacement. Then next coming to the local replacement algorithm. What do you mean by local replacement is the replacement the victim frame is selected only among the frames of its own process. So here what we are doing here in local replacement, each process selects only from its own set of allocated frames. It is not going to harm the frames of the another processes. It is going to select a victim frame from its own allocated frames here. So the number of frames does not increase here in the local replacement. In global replacement, what it is taking the frames of other processes, so the number of frames goes on increasing there. But here in local, it is only selecting from its own allocated frame set. That is why here the number of frames are fixed here. They do not change while executing here. So here page fault can be controlled because it is selecting only from its own set of allocated frames. So this is the difference between the local and the global replacement algorithms. So then suppose we are having a multiple processor environment here. So when this multiple process environment is present, we can share the data between the different processes. Is it not? So we can share the data between different processes from different CPUs also. Suppose there are 3 CPUs here. So means there are 3 processors P1, P2 and P3 here. If a process from processor P1 wants some data in its own processor, then it can access it faster. If it requires the data which is present on another processor, then some delay will occur, because this delay occurs because of the interconnection of those processors and the memory. If we are going to get the data which is very near to the processor, the access time will be very less. If we are going to get the data from a memory which is away from the processor, some delay will occur. So this is called as non-uniform memory access. What is non-uniform memory access? The time delay which happens while getting the data from the memory which are at different places. So that is called as non-uniform memory access. So if the time taken to access the data is the same at all the places of the memory, then it is called as uniform memory access. If the time taken to access some data from the memory is different, then it is called as non-uniform memory access. Due to non-uniform memory access, the system becomes slower and the throughput and the execution time also takes more time, and throughput also decreases here because of the different interconnection in the system. That is why non-uniform memory access takes place. So next and the last concept we are going to study here about the thrashing. So before understanding thrashing, let us consider a situation here. So the operating system is monitoring the utilization of the CPU. Okay, if the CPU is underutilized, means if the CPU is staying idle for some time, then what the operating system will do? It will increase the utilization. How? By introducing many of the new processes. So once many of the new processes are used and global replacement is used. What is global replacement? It is choosing a victim frame from globally from any other process also. So when the CPU utilization is increased and global replacement is used, that time a process is taking a frame of some another process. One process takes a frame from some another process. At that time what happens here? Page fault happens because of the another process. For example, P1 is taking a frame from P2. So P2's frame is given to P1. P2 is falling short of a frame now, is it not? One frame has become less in P2. So it is when a page fault occurs, so again what happens? Among its own page frames is going to replace. So more and more page faults happen. So when page fault is increasing due to this global replacement, what will happen? CPU utilization will become again less. Why? Because the processes wait for the paging. Is it not? During the paging there is a delay. So when there is a delay because of this global replacement, CPU will be idle. Again operating system will see that CPU is idle. So again it will introduce the more number of processes. When more number of processes again are brought into the system, what will happen? So again Global replacement causes the page faults to increase. So this increasing activity of the page fault results in thrashing. Thrashing, what is thrashing? Thrashing, whenever there are no enough free frames to support the active pages of that particular processes, page faults occur subsequently. So, and when this high paging activity takes place, that situation is called as thrashing. So, how do we control this thrashing? The name itself says it is something which is vigorously happening. That is, when high paging activity takes place, thrashing also takes place. So how do we avoid this thrashing is, one is by using global replacement algorithm. So if we use the global replacement algorithm, then the processes will just select the frames from their own set of allocated frames. They are not going to take the frames of another processes. So this is one method how we can decrease the thrashing here. Another method is in the allocation of a frames itself, finding the working set of that particular process. What is that working set strategy? Working set means the minimum number of frames which are required to store the active pages of that particular process. That is called as the working set strategies here. So what this working set strategy says, it states that a process during its execution, it moves from one locality to another locality. Here what is locality? Locality means a set of pages that are actively used in that particular process. So from when the processes change, so the state of the process moves from one locality, one set of pages to another set of pages. So by using this theory, we can set up a working set module. So this working set module will define the total number of active pages at the moment. So when you are getting the active pages, we can give the number of frames depending on that active pages to that particular process. And this is represented by a parameter that is delta. Let us here with an example. So this is a memory references string here, 2615 51623 This is a memory reference. Now if I consider at time t1 from 2 till 1, what is the working set? Which are the active pages? The active pages repeatedly used here are 1, 2, 5, 6 and 7. Okay. So depending on this locality, this is a locality now. So it is a set of pages which is used for this time t1 here. So at this time it is in this locality. At time t2 means I am measuring at time t2 this much locality. In this locality, what is the active pages here? The active pages are only 3 and 4. Repeatedly 3 and 4 is used. Now you can see here at time t1 our working set window was having 1, 2, 5, 6, 7 active pages. At time t2 it is being decreased to 3 and 4. Means during the execution of its process, the process is moving from one locality to the another locality. So this is found out by using the delta parameter there. How to set this delta parameter? We have to set the delta parameter, which we have to find the locality. So if the locality is very small, like this now 3 and 4, the locality is very small. If for the whole process, if I choose the window as 3 and 4, what will happen? This locality cannot be covered here, is it not? Because here 3 and 4 is not present, this locality cannot be covered. Suppose if we are having very large window, so if we are having very large window, the localities will overlap. So choosing this window is also important. So that is working set size we have to find out. So that is the demand for the frames can be found out by the working set size. So working set size of the ith process is given by summation of this one, working set size here. Currently how many pages it is requiring in the complete memory reference? Here it is requiring 1, 2, 3, 4, 5, 6 and 7. So what is this one? Summation of working set size here is 7. So D is equal to 7 means total demand of the frames here will be 7 frames according to this localities which We have this is one locality, this is one locality. So this is one working set, this is also another working set. Summation of these working sets will give me the total demand of frames here. So depending upon this working set size, we can allocate the frames to it. Then another thing is we can set how we can minimize this thrashing. So one is by setting this working set size, finding the working set size and setting the delta parameter. Another is you are putting the limits. So putting the limits on the page fault frequency. So what is page fault frequency? Total number of times the page fault is occurring. That is page fault frequency. Upper limit and lower limit, or upper bound and lower bound you are setting here. So when you are setting a upper bound, if a process exceeds that upper bound, if a process exceeds the page fault of a upper bound, then page fault are happening more. So what you do? You allocate a frame to it. So when you are allocating a frame to it, directly in a free frame, that new page can be stored so that no replacement takes place. So paging does not take more time there. So hashing happens because of paging activity only. We have to reduce the paging delay here. How to reduce the paging delay? We are supplying the new frames here. So by supplying the new frames, we are reducing the paging activity. Suppose now if it is the page fault frequency is going below the lower bound. So when it is going the below lower bound means what? Page fault is page faults are very less. So when the page faults are very less, what we are going to do? Take the free frames. Simply the frames are being wasted. Page faults are happening very less. So it is that process is having more number of required free frames. So what it will do is it take that free frames which are present with that process. So by doing this, by monitoring the upper bound and lower bound, again you are reducing the page fault. When you reduce the page faults, what will happen? The paging activity delay is also reduced. So when delay is reduced, then hashing does not happen there. So these are the two methods: by setting the working set size, finding the working set size using the delta parameter and the demand of the frames, and putting the limits on the page fault frequency. By doing this, we can reduce the thrashing.